This podcast is supported by Siemens, your partner for industrial-grade AI.
Hello, everybody, and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber, and we are back from our holiday break. Hello, Peter.
Good morning, Robert. How are you doing? How was your holiday?
Oh, I'm doing well. I spent 2 weeks at the seaside in France, and now I am already on my way to Berlin again for Frank Hütter's Auto ML conference. So I quickly washed my shirts yesterday, and I am off again.
Oh, that sounds great.
Yeah.
We're going to have our event with Frank. When is that? Is that November time or?
October. I have good news. We are fully booked. You heard it. Our event in October, AI in the Forest, which we are hosting together with Hannover Messe, is fully booked. But of course, we are planning a few more events for next year. If you want to make a reservation, just send us an email. And now back to the news section.
We are fully booked already. The conference where you today is relatively big, I believe, actually.
It's very big. I think it's a whole Auto ML academia community is coming to Berlin. And the conference is until Friday. So it's a whole week Auto ML.
You're going to be there all week or just
No, I will be until Wednesday. I will be there, yeah.
Okay, you can tell us all about it in 2 weeks when we talk again.
Yeah, I think it's very interesting because there are a lot of discussions bridging the gap between Auto ML, academia, and industry. It's very, very interesting. There's a focus on industrial or on industrial applications in Auto ML, yeah.
My brain starts thinking again. When it starts thinking that, maybe Frank and his team, who kind of initiated the complete AutoML movement as far as I am aware, maybe they were really a year or, well, I guess more like 5 years ahead of what then was called and still today is called AutoML. Maybe today has moved further a step, and it's called generative. It's in the same direction. And I'd say generative equals AutoML or the other way around.
Oh, there's a discussion also about LLMs and AutoML, yeah.
Most certainly, because it's all about this democratization of data, of algorithms, making them available in the hands of those people who until now, did not study or learn how to program.
There's a keynote from Andreas Müller from Microsoft, and the topic is from AutoML to AutoDS, Auto Data Science.
Oh, well, there you go.
Is that the future? I don't know.
Yeah, I think that is going to be, we're in the very middle of it, I believe. Yeah. So, in the end, it's going to be about what are we going to call it? I just saw this, I used the term Gen AI. I'm not sure what you think of it. Generative AI. I used it in an interview I did last week. I also went on holiday. But then again, I must say that wherever I am in the world, there's always a little bit of work to be done, so to say, always looking of what's happening. But I used it in an interview I did with Kurt Demarche. He's the co-founder, chief AI officer at Side Machine. So you will hear it in a couple of weeks.
What's that?
Side Machine is an important provider of AI predictive maintenance solutions to the industry. So you're going to hear about, again, all about democratization, bringing the solutions closer to the people in the factory floor.
Oh, perfect. So you mentioned you were not on holidays, or you were on holidays?
I am, but then I was, and then I am, but there's not such a big difference. When I think back of when I was a kid and, living in the Netherlands, and we would go somewhere actually in Germany near Koblenz, I believe, close to the River Lahn.
To the mountains.
Well, yeah, for us they were mountains, of course, because we don't have any. Well, we need to be careful. We have some hills in the Netherlands.
Yeah,
and then there was this time frame of 3 weeks. And at the end of the 3 weeks, you were really sad, right? You had spent your time with these other kids and you were really, really sad, kind of. And that was this time of the year. And if I compare that, for me, as I say, wherever I am, if I'm somewhere else, not where my fixed living place is, and maybe you call it holiday kind of thing, but I still open up my notebook at 6 or 7 in the morning and see what's happening. So that I'm not saying I'm working all day, but there's just not this clear difference between what is the working time and what is. And I think that's for many people these days. You need to be careful, of course, that you do spend free time doing other things than what you typically do for work.
And you did an interview with Professor Dr. Oliver Niggerman, right?
I did that as well.
Yeah.
That's what we're going to hear about today, right? After we are... I can tell a little bit about it now or later.
Sure. Yeah, now.
Yeah, I mean, he did a paper together with two of his colleagues. It's Alexander Windman, he's a research associate, and Henrik Steude, he's a ML researcher, PhD candidate, both at the Helmut Schmidt University. Oliver has been with us 1-2 times. You can hear about it also in the interview. And they wrote a paper. It's about robustness, generalization, performance of deep learning models on cyber physical systems, a term I asked Oliver, of course, at the beginning. I think it was strongly related to the introduction to Industry 4.0, right? But in the end, what they do is they look at a different deep learning model architectures. So there's recurrent networks, LSTM, convolutional, but they also look at transformers. And how do each of these behave in cyber physical system? Let's just call it as an example in your production line. So I think very important, they look at robustness against the services. They look at capability of each of these different types of machine learning approaches to generalize, to transfer, and the influence that data augmentation can have on each of these. So I'm not going to tell you what the outcome is. Happy listening for all of you, but it's very interesting, the outcome.
I think it's very interesting because I never fully understood this robustness issue. How do you make a deep learning model more robust?
Yeah, and without going into the details and not being the specialist anyway, because that's what these guys, as an example, are. That's how you compare the different algorithmic approaches. I can recall from experience with the specialists around me that it was always depending on the quality of the data you have. You have real good data. In the past, that was not very typical, but it's changing and changing again, right? Again, if we say we have OPC-UA, just as an example, then the data is implicitly almost perfect, because if not, your facility could not be running on the basis of the data if you have very bad data. So depending on the quality of the data, your data science specialist will tell you that a certain algorithmic approach can still work or will work fine, filling in itself missing values as an example. And another algorithmic approach will just stop. We'll say, we'll be like a certain human that says, no, I don't feel like it. I'm not going to do this, something like that. So again, I think that depends a lot on the different algorithmic approaches. And that is the idea. They're going to give you as a listener who will be using, or maybe some of you, many of you, I believe, who are the decision makers, to say, okay, should I consider using transformers and for whatever approach or not? Or should I stick to the convolutional network? Should I be using LSTMs, etc.? And they look at these different approaches and they tell us what you can do with it.
Oh, that's interesting. We will link the paper also in our show notes, I think, yeah?
Yeah, most certainly. So what we can still do, I looked at important things that happened while we were out. If you want to, I can share 2-3 of them.
Sure.
You can, I'm sure, I try to leave you alone as much as I could. I think I did, actually, most as I could. But I'm sure, knowing you, that you spend, 5 or 10 minutes every day as well. So what did I see? I saw still in these, what were they, a couple of weeks that we were out, we did a pre-record 1 or 2. I think there was an array of new upgraded large language models and related announcements. There was Meta. They released, I think in our time, Llama. Is that how you call it? LLAMA, Llama, and Code Llama open source. Also very important for your open source podcast, I guess.
It's not mine. It's all of
Oh,
us.
yes. Well, the one that you are doing with. I mean, this topic is always there, and I can only say in relation to Meta, what I see the people talk about it, people that know a lot more about it than me, that they're very, very positive about. In this case, Meta had a couple of false starts, I would say, in the last half year in relation to large language models. But now people are very, very positive about what they're doing with this one. So, and I do not want to go into the details because I'm not the one. That's what I'm saying at the end as well. There is the Technology Innovation Institute. I talked about that when I was at Hugging Face, you may recall, because they're from Abu Dhabi. Remember I said I was going to go to the Hugging Face site and look at all these, 100 different large language models. And the first one I saw was that. And that's not a coincidence. I'm going to come back to that in a moment, because they released what is called Falcon 180B. That's how you pronounce it. Then there was an Anomaly GPT. That's a paper by a group of Chinese researchers. And that's, of course, closest, I would say, to what I've seen to us here in the Industrial AI podcast. Was shared by Stefan Sulak, and that's for detecting industrial anomalies. There you go, using large vision language models. I think we need to look into that in more detail. Maybe we're going to ask one of the Chinese researchers or Stefan, somebody who is a specialist on the topic, because that's a very specific use of LLMs in our specific area, right?
Absolutely. I have another one, a personal announcement. I think I also shared this with you. The Sepp Hochreiter from JK Linz and his staff is bringing back a top researcher from Microsoft. There was this news, and Johannes Brandstetter is coming back from Amsterdam to Austria. So welcome back, Johannes, to Austria.
I saw that, yeah. I'm still waiting for Zep, or maybe then for Johannes to co-announce, who knows, because he's been looking for a way to bring his solution. I think he talked about it a couple of times. He talked about it at our big event, but then he has gone live with this idea for a couple of times, I believe, right? That he is looking for, what is it? He needs training capabilities,
yes.
right? So he needs, and I believe in the size of a Microsoft, there's only a handful of companies who are capable of doing the training of the big large language models, if they're Microsoft or AWS or Google, and we come to now, some companies in Saudi Arabia. I haven't heard, but that's a very good sign, yeah, very good sign.
Yeah, but Johannes is not in our main focus, because he's focused on simulating climate change, natural science. So it's more another direction, not the industrial sector.
Right. But I could, I am actually now simulating, or, sure. I believe whatever approach SAP has in mind, I'm sure that it can be used for any of the different market segments. Doesn't matter if it's climate or industry or whatever.
Yeah.
Then we had Andrew. That was very interesting as well. Andrew Wang asking, dear friends, do large language models understand the world? I thought that was very, well, what should I say? I do want to read his quote. As a scientist and engineer, I've avoided asking whether an AI system understands, quote unquote, anything. There's no widely agreed upon scientific test for whether a system really understands, as opposed to appearing to understand. Just as no such test exists for consciousness or sentience, as I discussed. And then he says, this makes the question of understanding a matter of philosophy rather than science. But with this caveat, and now it comes, he says, I believe that LLMs build sufficiently complex models of the world that I feel comfortable saying that to some extent they do understand the world. Now you're quiet.
Yes, and this is so. I think it's a typical, LinkedIn post. Can systems understand this and this and this and yeah? I'm
sure,
tired
but then,
of that.
Yeah. But then Andrew is, he's not. He is one of the persons who should be and is on this list of what the Time 100.
Yeah.
AI people. Many, many, many other people that should have been on there, to my opinion, are not on there, and other names of people who you've never heard of. It's always like the top 100 of what should I say, songs. Yeah, well, and it's whenever you go far back, let's say rock and roll and stuff like that, and then there's some piece of music which came in a half a year ago, and people have been playing it for half a year, and sure, probably a good song and important, and it suddenly appears on that list, whereas there have been, probably 100,000 other songs that were more important, so to say, and that's the same with this people. And then we just mentioned only one name, and the second one is going to come up. These people who have laid the groundwork of where we are today, and many of them are not on that list. So
what else do you have?
I have one more,
yep.
Because it's Saudi Arabia and United Arab Emirates. They secure NVIDIA GPUs, race to build, So what are they doing? They have a vision. They call it Vision 2030 in Saudi and Vision 2031. So they want to transition their economies away from the oil industry, right? So, and in Saudi Arabia, and that's where we come to the second name, they purchase was done through KAUST. That's the King Abdullah University of Science and Technology. And this is where Jürgen Schmidhuber is director of the AI initiative. So, and what is important for me is then with all these large language models, there's a growing number of folks like on LinkedIn that start explaining, like consulting us, the users, on the different specifications on the USB. So yeah, I do have a couple of other things, but we can do that next time as well.
Absolutely. So I now will catch my train to Berlin, and we will go into the main part and listen to Professor Oliver Niggemann. Thanks a lot, Peter.
Peter, Robert, have a nice trip on the Deutsche Bahn. Is that what you're going with?
Yes.
Okay, good. Enjoy your time.
Keep fingers crossed, yes.
We'll talk again in 2 weeks.
Thank you. Bye-bye.
Thanks. Bye-bye. My name is Peter Seeberg. My guest today is, once more, Oliver Niggemann. He is professor at the Helmut Schmidt University. That's the University of the Armed Forces in Hamburg. And as far as I know, and Oliver will confirm, it's one of the two in Germany, and the other one close to where I live. Oliver's area of expertise, machine learning, artificial intelligence for cyber physical systems. And today, Oliver and I are going to talk about robustness and generalization performance of deep learning models on cyber physical systems. Good morning, Oliver.
Hi, Peter. Nice talking to you again.
Yeah, please introduce yourself to our listeners and let us know in a little bit more detail than what I just said, what you do at the Helmut Schmidt University.
Yeah, you're right. So we are one of two federal universities in Germany, which is very much focusing on the armed forces here. But we do general research, and my focus is AI and machine learning, especially for cyber physical systems. And so we are very much involved in developing algorithms which are robust, which are suitable to be employed in technical machines, in ships, in spaceships, whatever. So our focus is getting those algorithms into real life machines.
Okay, and that's exactly what we're going to be talking about today as well. Now, today is not the first time that you are with us. Do you recall when you have been with us on our podcast and what we talked about?
No, actually, I'm thinking about it. I don't remember, but I think now it has been a while.
It has been a while, yeah. The last time was episode 84. That was February of 21. So that's 2 years ago, more than 2 years ago. And it was about how do I get synthetic data? But that was not the only time. You were there before, a year before, actually, in March 2020. So more than 3 years ago. And that was episode 43. And you talked about machine learning approaches for the industry. So listeners who are going to be happy with listening to you today, there's more from Oliver if you want to. So Oliver, today we're going to talk about robustness, generalization, performance of deep learning models on cyber physical systems. What are cyber physical systems? For short, CPS. I'll use, and maybe you use the term intertwiningly. And where does the term actually arrive from?
So, I mean, the term is mainly used for all, let's say, automated control old systems. And now if you look at a modern ship, it's not only the physical ship itself, the machines or the engines and whatever, but it's also the computer software, the controllers controlling this. More and more, we have systems which work in a closed control loop. And those closed control loop systems are a mixture of hardware and software. And of course, by having such a loop, a lot of dynamic effects happen. And in such an often you have hierarchical modular systems. For example, a ship obviously comprises not only the engine, it also comprises the navigation part. And so all this interacts. And of course, it also interacts with the environment. For example, here we see conditions, weather conditions, etc. And this, of course, leads to systems which, of course, from a machine learning data analysis point of view, we talk about time series. We have a lot of variations. We have a lot of noise. We have a lot of very different modes under which systems act. For example, it's totally different whether the ship is in the harbor or whether there is like before 10 and the ship is sailing somewhere.
Okay, very good. Now, together with Alexander Windman, he's a research associate, and Henrik Steude, he's a machine learning researcher and PhD candidate at the university, Helmut Schmidt University, where you are. You wrote this paper, Robustness and Generalization Performance of Deep Learning Models on CPS, Cyber Physical Systems. So what can listeners expect from today's talk? Maybe give us a quick introduction, or maybe you want to share with us the research questions actually that are discussed in the paper.
If you nowadays have some technical systems, some production systems, a ship or a plane or whatever, and you would like to analyze some data, you're very often faced with a situation that you have dozens, hundreds of different machine learning algorithms. For example, you would like to implement an anomaly detection. You would like to identify non-normal situations, or you might face a situation that you want to optimize your system. And then currently, you still have very much, it's like, let's say, random search. You have some educated guesses. Let's use some algorithms and you give it a try. And if it doesn't work, but this is a very difficult task at the end of the day, which needs a lot of expertise. But it's not only the choice of the algorithm. The algorithm has hundreds of parameters. The training process can be done in very different ways. So getting this model, this machine learning algorithm to work is very tedious and it's very unreliable. And at the end of the day, we are faced with a situation in machine learning, in AI. We don't have a complete theory which tells us for this scenario, for this data, we have to need this algorithm with this parameters. We are missing that. So what can we do? All we can do is, let's say, in a systematic way, provide users some information. How do specific algorithms perform for specific tasks and for specific systems? And that's very much what we are currently trying to do. So, and this paper, for example, which you are quoting, is one of those works where we try to find some, let's say, typical application scenarios. In this case, it's a simplified application scenario, but then try to outline which type of algorithms have specific pros and cons. This is not like finding the best algorithm. There is nothing like a best algorithm. There is for a specific task, for specific data, the most suitable. And we always have to keep in mind, and that's why that's very much what we talked about robustness. It's also the generalization. If you have a production machine, at the end of the day, we won't be able to train separate neural networks, for example, for each small production module. This is unrealistic. People will only employ such technologies if they have some pre-trained or trained models. And this means we cannot always use the precise data from the precise machine to train neural networks. We have to use data and sensor data, for example, which stem from either related machines or to some extent maybe also stem from simulations. And that's generalization. Only if we use this data, it won't really fit 100% to this specific machine. It will be very similar. And so this model has to generalize for this specific machine. And this is very typical for technical systems, production, and all those application areas. And so that's why we try to analyze how do they generalize those algorithms.
Right. And today we'll talk about some of these pros and cons, as you say, like with regards to robustness and generalization of different algorithmic approaches. I guess in the end, the goal is always to come to what Boris Scheringer from Siemens has called industrial grade systems. So you introduce your paper by saying that deep learning has shown great potential for improving the performance, robustness of CPS. You just mentioned that by enabling systems to learn from data, adapt to changing conditions. Can you give us maybe 1-2 examples of that, please?
Yeah, changing conditions, it's very difficult getting enough data for all possible situations which might arise in a system. So the examples here are from process industry. And you always have like a point in time when it's a specific situation, opening a valve, closing a valve in relation to other valves. When that happens is you have an infinite number of possibilities. So sometimes an effect might occur a little bit earlier, a little bit later. If the system degenerates a little bit without causing problems, still working, the timing might change a little bit. Or, for example, sensors change over time. The noise might increase. And this is all normal. And if the models cannot take this into consideration, it works like for Monday and Tuesday. And then you're very proud, hey, I have an AI-based process industry system here. On Wednesday, you run into a problem because the environment conditions have changed, etc. And this is what we try to at least to analyze and to find solutions.
Very good. So we talk about deep learning. So what type of deep learning models have been used in cyber physical systems processing time series data, as you mentioned lately?
It's still a zoo. So you really have a zoo of different
Really?
algorithms. The large classes obviously are, let's say, all the typical vanilla feed-forward nets, which are still used, which actually perform for a lot of use cases very well. It's well understood. It's easy to train. So it doesn't always have to be the most fancier solution. As a researcher, I love, of course, fancy solutions. That's where I get my money from to some extent. But obviously for industry, a little bit older, reliable, well understood solutions like vanilla networks, multi-layer perceptron networks, etc., work well. So then, of course, the second big class we have are all the recurrent networks from LSTMs, GRUs, and we have all those networks. And they have a lot of advantages, especially if the system have memory effects, have states. And for other type of systems, convolutional TCNs, etc., work very well. That's especially if we try to identify specific patterns in the data. And then, of course, depends a little bit on the time scale of the patterns in the data. And they are the transformers. We have all this discussion about transformers currently for language processing. And of course, transformers are also applicable to industrial processes, to sensor data. And here, those are only like 4 typical classes of algorithms. In each of this class, you have dozens of variants. You just have to go to ICML, AAAI, HCI, and you will find dozens of new variants each year. So the question from an industry is, of course, they don't want 100 solutions, they want one reliable solution. And those different classes need totally different solution approaches. They have pros and cons. And so we try to analyze a little bit, and the focus is on a little bit. A lot of people are working on that. But here it's not find a new algorithm. For us, very often the question is, can we analyze the pros and cons of existing algorithm if it comes to robustness, industrial data, etc. And this is, let's say, you have more papers about new algorithms than you have about analyzing existing algorithms.
Right.
Now, I just try to convince my PhD saying, hey, it doesn't have to be the new algorithms this week. Maybe we can analyze those 3 important algorithms, for example, for process industry or for navigation data or whatever.
Which is sometimes forgotten in papers anyway, right? The relation to the existing outcome. I mean, just doing something new without saying what is the pro and con, as you say, or what's saying what is better than what we have been doing so far is not really useful. So yeah, so you did a setup, and we'll come to that in a moment, and then listeners can at the end learn from you what the pros and cons of the different approaches in the industrial environment are. But before then, what are the challenges, maybe more specifically deploying deep learning algorithms on cyber physical systems?
At least two big types of problems. One is simply training them so that they can be used in a closed loop. If I put a neural network onto a ship, then I have to be sure it still works if the ship is somewhere out at sea, and I won't be there. So if there's some problems arise or some new situations, it's not possible on the ship to say, hey, let's retrain a neural network. That occurs once, and then the skipper is never going to use it ever again. So our challenge really is with few data. We don't have billions of data points. This is not large language models we are talking about. Obtaining suitable sensor data in industry is very, very difficult. And so our task is really training robust models which generalize for maybe not all to new situations. All this requires, let's say, a lot of different approaches. For example, pre-training with simulation, verifying the networks, etc. And this is one of the big challenges. The second challenge we're also working with in some projects is then you can never be 100% sure. It's machine learning, it's data. You need like a second supervision system, which always checks, is the AI doing something which might cause harm? So you have to need a second level of security here. So it's also the environment in which you place those algorithms. You cannot simply take, let's say, a controller, start your 6.11.31 developing environment, and then put the method, the model, the method in there. So what you need is definitely some quality insurance, some security supervision system. And this is obviously, it's a second AI system to some extent, which checks the first one.
It's interesting you mentioned that. I didn't come up with it myself this time, but it's been almost like an old hypothesis of me that where the rubber hits the road, you're going to need that kind of, let's say, boundaries. And those boundaries you can choose them, I guess, as wide, as low, and as high as you want. And in certain systems, they shouldn't be very broad. But yes, I always assume that the outcome from the deep learning system should be within those boundaries. And if not, that supervisory system is going to say, okay, well, I'm not going to listen to the deep learning system.
Which is difficult because normally in a non-AI setup, cyber-physical systems, technical systems are normally developed using control theory, etc. Those approaches, there is an expert absolutely knows what he or she is doing. So you can be sure that the developed algorithms, by having an expert, by testing, by verifying the solution in a classical manner, the system is safe. That's how autonomy is reached nowadays. Normally, autonomy is a very good example for non-AI systems in a lot of use cases. And now if you put AI systems in there, we have to change everything. The environment, the platform onto which we employ this AI algorithms, the testing process has to change. So this really changes everything from a, let's say, development process point of view.
So then tell us a little bit about your setup. You simulate a 3-tank, I understand, system for evaluating robustness generalization. Tell us more about it.
In this setup, we used a very classical, well-known artificial scenario. We used a 3-tank system, and 3-tank systems are well understood. Also, so we can compare to other papers at that point. Of course, it's a starting point. It's a hybrid system. So it's a mixture of discrete control systems, like opening a valve, closing a valve. This is discrete. But you also have a lot of continuous systems, like the fluid level in a tank, etc. From a, let's say, a computer science perspective, it's a nice setup. And so we can analyze how does it change if there's more noise in there. If a valve opens earlier or later, does it influence the correctness of the algorithm of the learned model? And so we can check a lot of things. Of course, as a starting point, we need more realistic scenarios. We're working on other simulation environments. It's very hard. Of course, we also want to use the real data we have. We have, of course, ship data, production data. But this is difficult because you can verify your results with that, but you would like to analyze how does your model performance change if the timing happens later and later and later. In this realistic data is difficult. I cannot go to some process industry, let's say chemical industry, and tell them, could you please do me a favor, change the timing until you have a problem. For some reasons, they never would like to do that for me.
Yeah, you'd rather simulate it before, right? Yeah. Okay, so which models then specifically, you mentioned the categories in general before, but which models specifically did you investigate? So your models under test, I believe, as you call it, without going too far in the mathematical details. I did see there is enough for those of you listeners who are interested in that, but I think the majority of our listeners may not be interested in the too much mathematical details.
We definitely use the classic feed-forward MLP models. That's
MLP, okay, yeah.
Line, right? If you use a time window, then we have the recurrent networks. We use GRU as this example, which is normally a very good guess for industrial processes from a training perspective. We have convolution networks. We use variants of TCN, temporal convolutional networks, and we have two variants of transformers. So that was our setup. And even that, just to get an idea, Mr. Windmann and Mr. Steude, who mainly did all the work, it's very tedious because you have to be sure it's not a training process. I mean, you can, let's say, train 10 networks and compare the results, but that's not really very good scientific work. All the results obviously depend on the training parameters, on the training process, how many epochs did you train. So you have to analyze how sensitive is it to those different hyperparameters. So getting some reliable results is very, very difficult, and we're still working on that, making it more and more reliable and more comparable. Just finding a setup in which you can compare in a rather fair way different algorithms is very, very difficult. But at the end user in industry, those persons need maybe not some rules, some guidelines. For this kind of data, for this kind of process, with this kind of constraints, what is a good starting point? Should I use a TCN? And generally speaking, how much data do I need? What are drawbacks in data? To which effects in data is the algorithm, the training of models very sensitive to? All those are very practical questions, which are not really answered.
Yeah, but you did a start, and that's what I want to move to next. So maybe you can share with us some of the experiments results. Maybe you want to go into specific experiments, look at some of the pros and cons. You probably cannot share all of them here, or you want to move to the general conclusions. I'll leave that up to you.
Yeah, maybe some very general results, not only from this paper, but generally speaking from projects going on here. I think, first of all, I would always work with the starting point with a very simple feed-forward neural network, vanilla network, which uses the time window of sensor data. So you take like 5 seconds of sensor data and simply put it into the network. That's not the most sophisticated. That's a rather old-fashioned approach, but it's always, very often it performs very well. So we all know normally in many cases, it's the data quality which is decisive and not the details of the algorithms. And then you really get the training to work. Then you have a baseline. And if you have this, then if you have for a lot of systems, especially if they are state-based, if they have a memory, cumulative effects in there, then of course GRU, LSTM, etc. are a very good guess. And for other kinds of disturbances, for other kinds of generalization, if small patterns change, of course, convolutional networks also perform well. We always have use cases where transformers work well, but so far it's better in large language models. I think it has a high potential, but it's not really the first starting point for most of our industry projects to use transformers currently. There's a lot of research probably still needed to adjust those algorithms.
I've read that they typically have a problem with the generalization, the transformers in the industrial setting.
I think in all our cyber physical system setups, we have, in comparison to the number of different situations, in comparisons to the data we get. For large language models, you don't run into this problem if you just scroll the whole internet. You really huge data sets. And we don't get that. For industry, the problem is not the amount of data, but the amount of different data. If you have a chemical industry, it's at least in continuous operation, it simply repeats itself. And the variants are not very big because normally the control systems have the task to avoid a large variations in the data. So we have a different data configuration. And that means that these algorithms, which perform in other situations very well, sometimes have problems if we apply them to typical industrial data sets. And then maybe, let's say, using a little bit easier algorithms is better than trying to use the latest sophisticated methods.
Okay. So what are the implications of your conclusions for yourself, for others maybe?
I'm not really sure about that. It's a very good question. As a scientist, of course, my aim would still be that we go a little bit into a more industrial ML theory. Can we identify the decisive factors and how the implementation of AI solutions. We have also AutoML, which, for example, in hyperparameter search, etc., does a good job. But of course, there's more to this problem. We still have choice of algorithms, very general decisions we have to take, and data has to be involved. So data quality. So what we need is a little bit looking onto the data and also involving there. And we still miss a lot of metrics. How do we measure the data quality for such AI processes? But that's research which is going on. That's a theoretical, the academic approach. The practical approach would be, we need, I think, some white papers, some seminal papers, which simply give a user, if a user has those applications, process industry, ships, discrete manufacturing industry, and it has this task like anomaly detection, condition monitoring, optimization, what are good starting points? I think that would already help. If the people could start somewhere and then have like a guidance to say, okay, if you have this amount of data and these algorithms, you should at least have these quality parameters at the end. So this would be more like heuristics.
So are they all topics for future work, for future papers that we may expect from your students, PhDs, from other people around the world that can use your work? I've seen that you make your research available openly as well.
Yeah, sure. We try to make most of our research publicly available as far as it's possible. But we here in Hamburg do a lot of those things. But there are, of course, a lot of other working groups which are also working on that. In Germany, there are a lot of active groups in Berlin, in Dortmund, in Bonn. So you have a lot of people who work on this, let's say, industrial setup for AI. It's still this is really an area where Germany is still, let's say, can contribute. So with this industrial base, I think Germany has a lot of researchers which focus on these kinds of questions. There is an area where I think we can still compete. But of course, I have to admit that if you now look at big conferences, there are a lot of work from the US and from China, etc., which are also very, very good. So that's
and those conferences, they do partly concentrate on industrial, or are they typically technology conferences where then the industrial applications are in a minor situation?
It's still like that. At some points, for some conferences, it's better, but we still have the situation. If I go to a pure AI conference, I'm exotic because I focus on industrial setups. And if I go to, let's say, industrial conference, I'm quite exotic because I focus on AI. So here we focus on AI. We come from an AI perspective, from a computer science perspective, and focus on cyber-physical systems. So we definitely come from this side. But if you look at 100% of AI work, this is a minor setup. Even in Germany. After all the decades, we still don't have an academic scene where, let's say, industrial applications and academic research fits 100% together. It's still too work.
Although, as you say, in Europe and Germany, we do have many, many researchers in the area, but also, a light figure like Andrew Wang, I know, with a specific company is concentrating on the industrial environment. So I do expect that we will see further developments. Oliver, thank you very much for sharing your research. And as we just said, it's there for you, dear listeners, to use, the pros and cons that you have just learned. You can download the paper. We'll put the link in the show notes. And I think what Oliver is suggesting is that, you can use the code, you can use the simulation environment, and you, as well as will probably your students, Oliver, you can continue the work that Oliver and his colleagues, his students have started. So thank you, listeners that want to get in touch with you. Oliver can best do that on LinkedIn, Oliver Niggemann. And if you, as I mentioned before, the listener want to hear more from Oliver, episode 84, as I said, how do I get synthetic data? Episode 43, machine learning approaches we talked about today. But if you want to get even more detailed for industry, episode 43. Oh, and I hadn't mentioned yet, actually, Oliver and I have been involved in several AI data science trainings. Been a while, hasn't it, Oliver?
Yeah.
But one is coming up. It's from VDI. It's the Organization of German Engineers. And they have a data science engineer training over, is that almost like maybe 10, 15 days, I believe. I do the next 2-day introduction in October in Düsseldorf. Oliver does the 2-day module 3. That's called data analysis and machine learning in January 2024. Otherwise, if you, the listeners, have any questions, comments, as always, please send a short email to peter@ipod.de. I'm happy you stayed with us so far. Looking forward to have you with us again. And Oliver, thank you very much for having been with me, and hope to meet you in person soon again.
Yeah, Peter, as usual, has been very nice talking to you.
Thank you. Have a good day. Bye-bye.
Bye-bye.